software release. Up before was CUDA 4.2. This is both our toolkit and our SDK, like the compiler and the software that's available for it. So we recently launched our alpha version. So this is still preview that you can get access to today. And then I also want to talk about where we see CUDA going just from a software perspective and kind of where we see the hardware going as well. Again, we see that's CUDA by the numbers. This is kind of just our inspiration for CUDA. Again, we're more about what people are using our tool for. It's I say we make the hammer. It's really cool seeing what people actually do with this hammer. We have like our GPU technology conference every year. Lots of hundreds and hundreds of posters, people doing very cool research with our stuff. And so this is where we've kind of come up with what the soul of CUDA is. When it first came out, CUDA 1.0, it was just a compiler and some C code. That's all it was. Now we really see CUDA as the platform for high-performance computing. That's what we want CUDA to be, both from accessible high performance, so it's easy to program, it's not hard to get access to, and then actually being able to pull the full perf out of the GPU. As I was talking to him, with Fermi, it's hard to get the full perf out of the GPU. It's certainly possible, but it's tough, so we want to make that easier. And so this is where we came up with CUDA 5 to help with this. Some of these are both hardware dependent, and some are just pure software. First one is dynamic parallelism I'll talk about. GPU object linking, if you know what CPU object linking is, this is just that on the GPU. Our new Eclipse edition, and then GPUDirect, and then also talk about HyperQ, which you'll be interested in. So dynamic parallelism, what is this? To date, the Fermi GPUs and all the previous GPUs, they have to have the CPU to tell them what to do. They have to control their flow of execution. And this can be very complicated. This is just some random made-up example of showing how you transfer data, you have the GPU do some work, you go back to the CPU, it executes some more things, and then you go back to the CPU and executes more work. And you just continue this pattern until you get your program done. And this can be very complicated to program. Like writing Q-sort on a Fermi GPU is extremely hard because it's an if statement. You're going down one branch to the other, and it's a recursion, and it's extremely difficult. And we actually wrote it because we needed to benchmark it and see how fast it went. But it's really hard, and the biggest part is this divide between the CPU and GPU, actually coding this. So what dynamic parallelism is it allows the GPU to create its own work. It allows a single thread to launch an entirely new grid. So now you can have your control logic actually on the GPU. So like you would just launch one thread and one block, and then that thread could just spawn as many grids as it wants. So this is what dynamic parallelism. This is a really big step in computing because it both from the what's this next one? Yeah, both from the being able to keep the GPU busy, and also it's from the software perspective, it's a lot easier to write code with this. So again, each individual thread can launch an entirely new kernel dynamically, simultaneously, and independently. It doesn't have to wait on anything else. Very easy to write a fork bomb doing this. You could have every thread launch a grid. You'll quickly run out of resources. That can happen all simultaneously. It's all independent. And a good example of how this will help, say you're looking at this fluid simulation from a jet engine. You want to, you can do the coarse grid, but you're not getting much data out of this. Obviously not useful. So you crank up your grid, but now you're wasting a lot of computations where nothing's going on. But with dynamic parallelism, you could actually focus in as you find data to do the work. So you start off with a really coarse grid. You say, hey, there's nothing going on here. I'm just going to ignore it. But over here, I start to see there's more work, and you just get more and more fine-grained precision. And this, again, you don't need to go back to the CPU. You could do this before, but you'd have to. There's a lot of data transfer back and forth, letting the CPU decide what to do, and it just slows everything way down. Very familiar syntax. If you know CUDA, you can write this. It's all it is CUDA on the GPU. In this case, we have A launches and then B launches, and then within B, we're actually just going to call X, Y, and Z. And this is set up as you would expect, so we have to wait for X, Y, and Z to finish, because this is how we've written our code. And then once that's done, now C can actually run. And so again, this is the majority of the API calls you're used to writing. You can now do CUDA mallocs, you can do CUDA mem copies from the GPU, you can do synchronize. So basically, it's CUDA on the GPU as opposed to running it from the host. Simple LU example, again, something very complicated to write on the Fermi. From a software guy's perspective, this is horrible because you have to basically maintain, you have a CPU function and a GPU function. A lot of times they're in different files, and it's just very hard to wrap your head around. Where now on the GPU, it's just have all your control loops over here, you go, and then you just wait for the GPU to be done. And the best part about this, now you have the CPU can sit here and do whatever it wants. It's free to go off and do other work, whereas before it had to sit there and basically babysit the GPU to keep it busy. So this is a big thing about dynamic parallelism. Really good example, I'll show the video of it. For Fermi, we had an n-body system. It was 20,000 particles. Oh, that's not the right one. Go away. Where is it? I must have moved it. Sorry, hold on. Oh yeah, sorry, there it is. So we redid basically the n-body with this, with our new chip that was floating around. So this is, the lights are pretty horrible. Yeah, is this it? Yeah, just for this little demo. So this is the Milky Way galaxy, 3.5 billion years in the future, and this is Andromeda coming in. At that point, we will collide. They first swing by. This is simulating 280,000 particles. This is not an n-squared algorithm. This is an n log n because of dynamic parallelism. So what they're actually doing, this is actually paused while this is a video from our keynote, so he's talking right now. What it's doing is it first creates a bonsai tree, and it will keep going down until the other galaxy or the other particles are far enough away that we can easily estimate the interaction, because they're so far away that it's so minute that you can estimate it. But all the other ones, we actually want to do the real interaction, the real gravitational pull. And so once it has its tree low enough, it'll just launch a new grid to actually figure out the interactions and then update the position of all these particles. So in our previous example on Fermi, we could only do 20,000. And granted, it wasn't n-squared. Now we're doing 280,000 particles. And once this actually gets going, we'll actually see they'll do a wireframe. I wonder if I can skip ahead. And this is all just done on that single chip I was showing you. Oh yeah, there they go. So yeah, so 3.5 billion years, they swipe by each other, kind of launch a few thousand stars out into space. And then in about another billion years, they'll come back and form a new ellipsoidal galaxy. So yeah, here they're actually showing the tree. So you can see out here where nothing's going on, they're really big blocks. But as you zoom in, they get more and more fine-grained, because that's where the interesting stuff is happening. So this is the real power of dynamic parallelism. This just really would not be possible on a pre-existing Fermi GPU NV4. Yeah, so that's our new n-body demo. Let me see if I can swing ahead where they actually merge. Yeah, they've actually merged. And of course, we threw a nice little render on this, so there's some dust in the background, but that's what we'll look like in 4.5 billion years. And there's a good chance you probably actually can't see them. There's a bunch of stars floating out around here. There's about a 50% chance that Earth and the sun will be out there. Of course, Earth will be pretty hot by then, because the red sun is a giant, a red giant. But so that's the power of dynamic parallelism, and a really cool demo that we've been working on with a lot of these guys. Yep. Question?
So for the launching of other pronouns from Nsight one, is it the same stream, different streams, different ones?
It doesn't matter, because the stream is basically a software concept on the host side. On the GPU side, it's just more work for it to do. And then it'll just wait for it to come back.
Okay, so it could be on other devices.
It'll be launched on the same device. It won't go off to another device. Does that make sense? And so you can now do recursion, actual kernel grid recursion. I think we have a limit of 63 or 64 recursive grids you can actually call and wait to come back. This is a case my demo didn't work. So again, it's just data-dependent execution. So now you can actually, dependent on your data, decide what your code's going to do, which wasn't possible before. Again, recursive parallel algorithms. Now it's really easy to write Q-sort. Basically, it looks just like you would on the CPU. Big thing is helping to keep the GPU full. Today, it's really hard to get Fermi, keeping it 100% all the time. This is a big step towards creating that, and also dynamic load balancing. And then, again, from a software guy's perspective, this is much easier to program on the GPU for these complicated functions. And you can now also call library calls. So all our existing cuBLAS, our cuSparse, and all these can actually just be called directly from the GPU. Again, the data's already there, so you don't have to go back to the CPU. This one I'll blow through pretty quick. Basically, before we didn't really have separate compilation and linking on the GPU, which was really annoying, especially when you have big CUDA programs, because you have to recompile everything every time. We now have added this with CUDA 5. So this is pure software. You can do this on any GPU. It doesn't matter. And if you know what CPU linking is, this is exactly it, but on the GPU. The nice thing about this is it now allows people to, vendors to add, you actually have a library that you can call into and then have callbacks. I think I have a slide. Yeah, so you can actually have vendor libraries that now have callbacks just like you would on the CPU. So it's just kind of just catching us up to where the compilation of the CPU has been for a while. Inside Eclipse Edition, I think I already talked about this. We've had this ability of the debugger and the profiler on Visual Studio for quite a while. We've now added this into Eclipse, so especially if you're going to get a new Mac with the CUDA kernel in it, you now can use the Eclipse IDE, and this all integrates very nicely. And same with Linux. We have a Linux version. We still have the separate there's a separate profiler, visual profiler that you can use if you don't have Eclipse. But yeah, so this has made a lot of the Linux and Mac guys pretty happy. And we're back in the Mac, CUDA on the Mac. And this is, it's not GK110. This is so Kepler is a family, and then there's like litters within a family, just like Fermi is a family, and there's a whole bunch of different versions of Fermi. This has the first version, which I think was the GK107. So this does not, unfortunately, does not support dynamic parallelism. And these new features I'm going to talk about, that's only available in that chip I was passing around and beyond GK110. So the other one, GPUDirect. We've had GPUDirect for a while where a single GPU could directly access the memory of another GPU on the same node, and it could copy back and forth. We've now added RDMA, so now a GPU can actually talk over the network directly to another GPU. It doesn't have to go to the host like we used to. This is done through MPI. There's a few MPI solutions we're working with. So when you say MPI send, it can figure out from the pointers what GPU it is, whether it's on a different node, and it will all just work, for you. So you just write MPI code like you normally would, instead of having to do the complicated, go to the host, go to this host, and then go to the right GPU. So this is a big step for cluster programming. Again, easing that data management and minimizing it. So this table is just kind of a breakdown. Like I said, there's the GK10X is the first litter out, and then GK110. So these are the features available. I'll talk about HyperQ in a minute. That's kind of an important one. I should have a separate slide on. But so pretty much everything's available on GK110. Is not available on GK110 except for this RDMA. So we've added warp shuffle instructions. Now within an actual warp, a single instruction, you can separate data around. This is great for saving shared memory. So it's just in one instruction, you can transfer data all the way around. We've added a read-only cache. On Fermi, we had this as you had to use textures to do this, so it was pretty complicated to program. We've just opened up access to that, so now you just say something's read-only, and the compiler will put it in the cache for you. A much bigger register file. We've more than doubled the number of registers available to each thread. We've also, in Fermi, a thread could only access 63 registers at a time. We've now upped that to 255. So a thread can get access to a lot higher number of registers now. Plus, we have a bigger register file. We improved the speed of the atomics to global memory by about 10x. So now it actually makes sense. You can do some, there's a lot of algorithms that use atomics before. They just were too slow on the GPUs because the global memory is so slow. So now those are actually plausible now with our faster atomics. This RDMA I talked about, available on both GK10X and GK110, but only the Tesla version. We doubled the L2 size and the speed of the L2 cache, so our caching is a lot faster. You can cache a lot more. And then we also improved our ECC performance by about 60%. ECC, for those who don't know, is error correction and, well, there's error detection and correction, EDC. But this basically tries to catch random flips in your DRAM. Unfortunately, if you get a neutrino coming in that hits your RAM just right, it'll flip a bit. It happens all the time. You can't shield against it. So this ECC is a way to check that. It just actually is a checksum to see if a bit got flipped, and it'll replay the transaction to try to get it right. So very important if you're doing some really high precision. You can't have bits flipping, but it slows things down. So we've improved the performance quite a bit with Kepler, because it's important scientific research. So HyperQ, this is addressing your problem that you were talking about. Unfortunately, at Fermi, even though you had multiple streams that are all scheduling concurrently, it's possible it would all feed into a single scheduler on the hardware side. So a lot of times artificial restrictions would get put in place where even though two kernels were completely separate and didn't care about each other, it would wait for the other one to finish just because it's all going into a single pipe. And there's really not much way you can get around that from a software guide depending on your code. So what we've done with HyperQ is we now have it, and this also goes back to the dynamic parallelism. We've added this basically work scheduler onto the GPU, some new hardware, and it can now handle 32 concurrent streams, and these are true concurrent streams. It doesn't go into one scheduled pipe. Will actually really schedule your hardware, your kernels concurrently if they're not a part of each other. So HyperQ is a big deal. You now can have 32 processors or 32 cores talking to your GPU at once. So it makes it a lot easier to keep the GPU full. You can really keep it busy more easily. So that's HyperQ. Please try out CUDA today. Again, it's if you're interested. I think actually this may be down right now while we're trying to get our site back up, but it should be up soon. It is an alpha preview. You just have to be a registered developer and you have access to it. We're hoping to have the release candidate out later this year. And then, so that's how we get you all your features. Obviously, you need GK110, which nobody has access to yet, to do a lot of this stuff. The first about 25,000 GK110s are going to get gobbled up by Titan, and there's another supercomputer. So it's going to be a little while before us regular people can get access to a GK110, but hopefully by early next year. Definitely interested in your feedback. There's just emails you can, if you are trying CUDA 5 and you have problems or things you would like us to fix, please email us. And then, yeah, the release candidate should be out later this year. So that's it for what we've announced so far. Any questions on that before I go on to the future? Yeah.
Is there any plan in the roadmap to make these tools installable via RPMs? I know right now everything's via your installer script.
Yeah, I'm not aware of changing it to RPMs. Part of the problems is having to support all the different distros and different ways of.
Yeah, I mean,
it's.
When you're targeting HPC, we've got hundreds of these things to maintain.
Yeah, I've been asked that question a few times, and when I go talk to because a lot of our guys are Linux users, and it's too much work to maintain. We don't have time to maintain all the different ways of distributing these things, and the RPMs and the Debians, and it just becomes a lot of just extra work for us to maintain it. It obviously is something, I get that question a lot, and so I provide that feedback, so it may get added down the line, but I'm not aware of it being in the roadmap at this point. Honestly, we would rather those Linux guys go fix the bugs as opposed to making it easier to install, but obviously if we had infinite resources, we would. We just only have so many people. So that question does come up a lot, but I'm not aware of it being on the roadmap anytime soon. Anything else? All right. So where do we see CUDA going? So again, we really see CUDA being the platform for parallel computing as far as libraries. We release a lot of libraries. Thrust is a big one, which I didn't talk about before, which I'll talk about briefly. Libraries, the tools, the parallel Nsight, the compiler chain, and then the actual programming language. So we really want CUDA to be the platform so the ecosystem can build on top of us, and I'll talk about ways we're taking steps to help that. There's, people ask, is CUDA the way to program? There's hundreds and hundreds of open source programs out there, and we want to be able to let people to code in what they want in CUDA. There's obviously some names on here I don't want to say, but these are real languages. This is just off of olo.net, which tracks open source code. So there's a lot of code out there we want to make. We don't want to force somebody down a path to be able to execute on a GPU. So we really see this happening in three ways. First one is high-level code that gives you a lot of power. And one of these is Thrust that NVIDIA, it's open source, but NVIDIA maintains. And essentially, it's just, if you've ever done boost development or STL development on C++, it's that for acceleration in GPUs. Like here on the right, this is doing just allocating 1 million elements, randomizing it, copying it to the device, sorting it, and copying it back. It also supports boost-style extensions, so the _1, _2, so you can do SAXP in a single line on the GPU now. So it's really powerful. You can get a lot of code done, a lot of work done in a very short amount of code. So that's one way we see things going. Also, another way we see code going is very expressive parallel programming, especially with dynamic parallelism. So this is a lot to kind of absorb at once, but all this code is going to do, it would be a sparse matrix multiplication times a vector. And it does this by first using like C++ lambda style function. And then within that, it would be using dynamic parallel launches. So it would actually look at the rows, figure out, get rid of the zeros, and then do the launch, because obviously you don't want to times a bunch of zeros together. And it's another way we see languages going. Really powerful, expressive. So you can do a lot of work in a few short amount of lines. This is the way we see CUDA code going in the future. And then finally, OpenACC, another big one. For both Fortran and C. Unfortunately, like I said, C++ is coming, but it's a lot harder. We see this being another avenue that a lot of people take, so we're putting a lot of effort behind this. And a bunch of marketing slides on OpenACC. And then finally is domain-specific languages. This is another big area that we see a lot. We want to put a lot of effort behind. This is where it's really hard for a lot of people to express their problem in C or C++ or Python. For example, R is a very popular statistical program. We want somebody to write R and have it run on a GPU. This LITS, partial differential equation solver created by the guys at Stanford. We want them to be able to code in their PDE, which they understand, what they know, and then run on the GPU, instead of having to port everything to C, like a lot of MATLAB guys do. They get their algorithm working in MATLAB, and they port it to C, because it's faster. So to support this, we've now opened up our compiler. I don't know if any of you guys all know what LLVM compiler is. Have you heard of this? So LLVM compiler is an open source compiler. It's basically competition to, like, say, GCC. GCC is a big monolithic thing. It's spaghetti code all over. If you want to add a new language, you got to port it all through, from the compiler to the optimization to the front end, the back end. It's very monolithic and old and spaghetti. LLVM is very modular. They did a really good job of separating out the different parts of a compilation: the front end, the middle optimizations, and then the back end. So what we've done is we've basically added parallel constructs into the internal representation. So now, say somebody wants to take R or Java or a VBA, whatever they want to write, they just have to write a new front end that converts their language into the internal internal representation that LLVM understands, and from there, that'll just fall out to run on the GPU. So now anybody can take any language they work on and make it run on a GPU. And in addition, Anybody could write new processor support for this. There's already a CUDA x86, so CUDA can run on x86. I think PGI maintains it. There's no reason anybody couldn't write one for a different GPU. NVIDIA is probably not going to do it, but I suspect somebody in academia is going to do it fairly soon. And again, then all you have to do is just take the internal representation that everybody understands and just dump it out into your assembly language or your processor's machine code. So this is kind of our answer to the OpenCL, open source. Don't restrict yourself to NVIDIA GPUs, which is a lot. People get scared that NVIDIA goes under, or our next processor sucks. They're stuck with it because they've written all this code for CUDA. This is our answer to that. We're just opening up the CUDA platform so you can run it however you want. So this is already up there in LLVM. You can go get the code now. We uploaded it early May, and it's we don't allow other people to upload code to it. It's open source, but we're going to be the only contributors, just because it would be much harder to maintain that way. So you can go out and you can get the code and do whatever you want with it. You just can't upstream to it. Any questions on LLVM? This is the compiler Apple now solely uses for everything. Apple's now all pure LLVM as well. As we said, the future is really heterogeneous. We want to let people code in however they want, whether it's general purpose languages, directives, or DSLs. And so that's where we really see CUDA going, just being able to use it on any processor with any kind of language you want. We don't see it just being CUDA C or CUDA C++. We want people to be able to develop libraries as they want, tools, compilers, change. With LLVM, you can now write a just-in-time compiler very easily into your program. So that's where we see it going. As far as education and research, a big one is the computer science area. Again, like I said, that algorithms book doesn't exist. There's not common ways of writing parallel code. Also, the architectures. Right now, everything runs on Intel. That's not good for innovation. That's not good for putting competition out there. So we created this little development device. It's called CUDA on ARM. This isn't actually running CUDA code on ARM. There's a GPU paired with an ARM processor. A lot of people are really interested in this and using these small things to create powerful clusters. You're putting a whole bunch of them in instead of like one really high-end CPU. You have a whole bunch of these smaller ARM cores. So we now have this available. People can go register and get access to one of these. I think they're like $600 for one. But you can actually write. You have a GPU tied with an ARM processor, and then just continuing pushing the research in the domain science, trying to get past the brick wall we've been hitting. So I kind of blew through that one pretty quick. Any questions? So that's where we really see things going. Maxwell is going to be our next chip out in 2014. It should be much, much higher perf per watt. It's basically following the exponential curve we have with Fermi to Kepler. Like I said, perf per watt is the new perf. That's our target. So that's probably about 2 years out from now when the next chip comes out. How about you guys? What would help you? What can NVIDIA do to help your research or your development? Yeah.
So there are a lot of researchers and people that are trying to use GPUs for irregular memory access. Basically.
Yep.
So it's different from the data parallel, scientific applications that GPUs work well for.
Yeah. So regular access, people think GPUs aren't good at it for like random access. When you have random access, you're bandwidth limited, right? Because you're sucking in a whole bunch of bytes that you don't need per access. So it's a bandwidth limited program. And we've already seen from that first chart I showed my first program, GPUs are actually much higher bandwidth than CPUs. So you may have to tweak your algorithm a little bit, but they actually can be very good at random access programs. I have a really good presentation from one of our managers, the NVIDIA slides. I don't have a video, but he talks about a whole bunch of problems that are very sparse. They're very random access, and they actually get much higher speedups than they're seeing or getting good speedups over the CPU version. So you just want to make sure you structure your program right. You might have to tweak it a little bit, but you can get nice speedups on a GPU even with random access type problems. One option, but the first thing I always say is turn off L1 caching, because now you're going to global memory with 32 bytes chunks instead of 128. Is one of the first step optimizations you can make. Just as something, just with the compiler option, you can usually get some good speed ups depending on the type of program you have. Because when you use L1 caching, it reads at 128 bytes at a time, so you're wasting a lot of your bus on wasted data that you don't need. And by turning off L1 caching, you're only going into 32 bytes at a time. So a lot of times you're pulling in a lot less useless data. But just as an optimization. I'm not saying it's easy. I'm not saying it's easy. I'm just saying it's possible. It is out there. Just people say, oh, it's a random access. GPUs aren't good at it. I'm just saying GPUs can be good at it. It just may be hard to write. Question?
So have been people successful in parallelizing database queries and running them?
Yeah, big data is actually becoming a lot of interesting GPUs. A lot of data centers are now adding GPUs. It's like, say you have, a terabyte of data you want to search through. You just start giving chunks of it to different GPUs, and it's a whole bunch of very basic queries. It's not some super high performance, a very complicated algorithm. So yeah, big data is a area that GPUs are becoming very popular in.
Something like the NoSQL system.
I'm not sure that that's been ported to use GPUs yet. Yeah, I don't know of any commercial products. I think they're out there. I just don't know off the top of my head the actual ones that are using GPUs. But like the face recognition one I showed at the beginning, they're using the GPU to actually do the data search as well.
So is Kepler any better than Fermi in dealing with branching?
Say it again?
Is Kepler any better than Fermi in dealing with branching?
Branch divergence, it's about the same. I mean, it's the same problem, right? If you have 32 warps and half of them aren't doing any work, you're just wasting those threads. That's something we're trying to fix going forward to reduce latency of a single thread and also reduce the divergence penalty. But Kepler's about the same as Fermi in that regards, as far as divergence penalties, yeah. Any other questions? Well, by all means, if you have code questions or you're like say you're having trouble with your random access problem, feel free to send me emails. I have plenty of resources at work I can hit up and talk to. I also encourage you, if you don't know about GPU Technology Conference, just Google GTC 2012. There's like something like 500 hours of presentations and videos all available that you can go watch, from very specific domain science types of talks to very general, optimization techniques or working with the debugger or the profiler. It's all just available online. I don't think that got taken down with the attacks. Sorry, I'll get him first. Yep.
So, so the Rust is currently available.
Yep. It's full.
And it's for CUDA 4, CUDA 5, just CUDA.
No, it's CUDA 4 as well. It's supported on CUDA 4.
Yeah. And the other thing is, for Parallel Nsight, is it possible to do remote debugging or?
Remote debugging? Yeah. Yes, it is possible. Yep. And actually, like when if you're like on the Windows side, you're technically doing remote debugging. You're just connecting to localhost. So yeah, it should be possible. And the nice thing about the Mac and Linux version, since it's their third-party compilers or third-party debuggers, you can actually get a stack trace that includes the CPU.
Because at some point I tried from Windows to Linux machine.
I don't know if you could go from Windows to Linux. I think you would have to go from Linux to Linux.
Okay.
I don't think you can go between OSs. I don't believe that's possible because the Microsoft stuff's not going to know how to talk to Linux and vice versa. But you should be able to go from same OS to same OS. Go ahead.
My question is about the energy efficiency. I mean, as you said, GPUs are very energy efficient. But kind of going back to my original question about the memory accesses, even if you port your code over to GPU and you don't get much speed up, is it possible that you will have degradation in energy efficiency? Like even, or I mean, you can always have degradation of performance and stuff, but is there sort of like, well, 0% improvement, but at least you'll get like 50% energy efficiency? Is there like?
It's certainly possible. It would be really dependent on the code and the algorithm, what it's doing.
But can you get like worse energy efficiency? Like that?
Oh, I'm sure you could. You could definitely write code that would be far less energy efficient. It would really just depend on the algorithm. I mean, if you're just constantly ping-ponging back and forth to memory and running a bunch of, it would definitely possibly be less energy efficient. I think it would be harder to do to write the code to be less energy efficient because GPUs are already good at that. But if you're porting an algorithm that's not meant to be ported, it's not going to work well. If you're porting, if you try to run an OS on a GPU, it's going to be horrible, burn a lot of power, and be very slow because that's just not what it's good at. So, but yeah, feel free to send me if you have like pseudocode or even just roughly what you guys are doing. You can send me an email and I can look at it. And we have plenty of guys that are. We have guys that are called dev tech guys, and they're very specific in different domains, and they're very good at writing code. They're basically CUDA ninjas, so I can always ping them. And
So that profiler tool, where you identify the bottlenecks.
Yep.
Is that relatively new? Because I've never heard. I mean,
no, it's been around for a while. It's been in the one that's integrated with the IDE was only on Visual Studio for a while, but we've had the separate NVVP. It's just NVIDIA Visual Profiler. That's been around for at least CUDA 4. And there's a command line version called NVProf that will, you just run it and it will dump out a data file that you can then look at with the profiler. So even if you're running on a cluster without a head, you can still get the data. So yeah, it's just called NVVP, NVIDIA Visual Profiler.
So when a GPU task launches another GPU task on Kepler,
Yep.
is that considered to be kernel or two kernels being loaded?
So if a thread launches a new grid, it's entirely new kernel.
So it has to be a new grid. So
Well, otherwise it would just be a function call within that kernel, right? So yeah, it will be an entirely new grid.
so say, for example, if you say in OMP parallelism, the thread can actually impersonate one of the like child task thread.
Okay.
Possible on Kepler.
I'm not sure. I have to see what you're talking about. Yeah, I mean, all it is it's just you're just launching a new grid. It's just like you had gone back to the CPU and the CPU had called a new kernel. It's just now you don't have to go back to the CPU. You can just have that single thread launch a new grid. So it just goes into the pile of work that needs to be done. So there's a new work scheduler on Kepler, and it just goes into the pile and says this is new work to be done.
So that would count against the 32 kernel limit.
The 32 kernel limit.
So I believe you said that there.
No, there's now 32 new. You can now have 32 processors talking to the GPU at once. Before it was 16 on Fermi, but it was all piped into that single scheduler. Now with this, what we call hyperqueue, you can have 32 processors all talking to the GPU at once, and it's not piped into the serial process, in this serial scheduler. It's just one big work scheduler that'll just round robin go through and do the work. So that when you launch a new grid, it just goes back into the pile. So it's a lot easier to keep Kepler busy.
So in theory, there's a much larger number of different kernels running on the Kepler.
Correct, and that you could theoretically get that many on Fermi, but in practice, it was almost impossible to do. All right, well, thanks, guys. Thank you for your time. I appreciate it. Like I said, if there's anything you think NVIDIA can do to help you guys in the future, I just got some good feedback already, but feel free to send me an email. It's kind of my job is to go out and talk to developers and see how we can help you as well as divulge information. So thanks for your time.